are in the series of quantum technology. In this series, we are discussing the quantum sensor. In the last lecture, we have discussed the what is a quantum sensors and how it works. Now, in this lecture, we discuss the types of quantum sensors. Basically, experimental implementations of quantum sensors based upon its action, like neutral atoms, how we will use, and what are the qubits we are using, what we are measuring, we're measuring quantity of this sensor, and what is the typical frequency we are using for the particular sensor. After that, we use a initialization. After that, we are having the readout value and the type of quantum sensor. We have defined the three types previously. So, on the basis of that, we can characterize these quantum sensors in the 1, 2 or 3 types. So, first we are discussing the neutral atoms. So, neutral atoms having the part atomic, vapor, cold clouds. Third is the third we are having the implementation. So we are having the various types of neutral atom. So we will discuss the neutral atom, how we use and how many types of neutral atoms are worked as a quantum sensor. So neutral atom as magnetic field sensor. Neutral atom magnetic field sensor means we are measuring the very sensitive or very low magnetic field by using the magnetic field sensor. For that, we use the neutral atoms. So alkali atoms are suitable sensing qubits. That's why we use neutral atom, because neutral atom acts as high precision magnetic field sensor, often revealing squid detectors by utilizing optically pumped atomic vapors or individual atoms in optical tweezers to detect the Zeeman shift. It means it works upon the Zeeman and Stark shift. So they offer superior sensitivity for mapping magnetic gradient using microfabricated chip structures. So enabling advancements in the quantum simulation, sensing and fundamental physical research. We just have the atomic sensor, that is also known as the atomic sensor. So what are the key aspects of neutral atom magnetic field sensors? First, individual atom sensor grids. So individual atom means individual atom trapped in microlines generated tweezers that can be arranged in arrays to map external magnetic gradient with high spatial resolution. In this series, we also have the optically pumped magnetometers. So, this OPM, these sensors use a light which is in the form of the laser to interact with the atomic vapor. Means whenever we talk about the optical pumping, so we use a laser light or any optical light just to interact with the atomic vapor. So where external magnetic field cause detectable changes in the optical signal. So acting as the ultra sensitive sensors. Next is the chip based technology we will use in this type of atomic sensors. So chip based technology means we are utilizing the atom chips. Neutral atoms are held and manipulated microns above the surface using the microfabricated structures to measure the magnetic field. So in this regard, chip is used. Another is the synthetic field. Techniques allow neutral atoms to behave as if they are changed, parameters, and it is by the charging the particles and creating the synthetic magnetic field to simulate phenomena like the Hall effect. Another is a high sensitivity. These sensors are at the forefront of the quantum sensor technology, so approaching the performance of established that squid technology, and these are very high sensitive sensors. What are the operation principle? Neutral atoms possesses a magnetic dipole moment which allow them to couple to external magnetic fields. So the energy levels of these atoms shift based on the strength and direction of the magnetic field, so which is measured using the laser spectroscopy. So the operation of these atomic sensor based upon the energy levels of atom shift based upon the strength and direction of the magnetic field. That is the Zeeman effect, and that can be measured through the laser spectroscopy. And these neutral atoms possesses a magnetic dipole moment, which allowing them to couple to the external magnetic field. So their ground state is in the form of the spin. So a coupled angular momentum of electron and nuclear spin can be both prepared and read out optically by a strong spin selective optical dipole transition by linking their wave electronic ground state and the first excited state, that is the S wave and that is the P wave respectively. So what are the sensors which based upon the neutral atom? First is the atomic vapors sensors. So in the simplest implementation, a thermal vapor of atoms serve as a quantum sensor for the magnetic field. So held in a cell at about room temperature, atoms are spin polarized by an optical pump beam. So we are talking about the simplest implementation of this atomic vapor, where we are just using the thermal vapor of atoms, which are used as a quantum sensor for detection of the magnetic field. So held a cell at or about a room temperature, atoms are spin polarized. So this spin polarized can be done by the optical pump beam. So magnetic field sensing is based on the Zeeman effect due to the small external field orthogonal to the initial atomic polarization. We are having the atomic polarization, and so we are having the magnetic field sensing, which is based upon the Zeeman effect. But in the classical picture, this field include the coherent precession of the spin. But here what are we are having? We are having the spin polarized because of the optical beam pumping. So equivalently in a quantum picture, it drives the spin transitions from the initial quantum state to a distinct state, which can be monitored by a probe beam, for example optical Faraday effect, and in this manner we can detect the magnetic field. Despite their superficial simplicity, these sensors achieve the sensitivity in the range of 100 atomic Tesla or root hertz. So and approaches the theory limited to the less than 10 atomic Tesla. So placing them on par with the superconducting quantum interference device as the most sensitive magnetometer up to now, that is a SQUID. So this is owing to the surprising fact that relaxation and the coherence time of the spins in the atomic vapor can be pushed to the second to the minute range. So relaxation and the coherence of the spin participate in the detection of the magnetic field of the atomic vapors. So these long relaxation and coherence times are achieved by coating cell walls to preserve the atomic spin upon collisions. So all the cells are coated, cell walls are coated just to preserve the atomic spin upon the collisions by operating the spin exchange relaxation free regime of high atomic density and the zero magnetic field. So a high density suppresses decoherence from atomic interaction, since collisions occur so frequently that their effect average out. That's why it is coated with the some polished way. So similar to the motional narrowing of dipolar interaction in the nuclear magnetic resonance. In the vapor cells that are having the miniaturized to a few millimeter cube with a small volume and have been used to demonstrate the entanglement enhanced sensing, means while narrowing or miniaturizing up to a small volume, it is easy to demonstrate the entanglement and enhance the sensing process. So the most advanced application of the vapor cell is the detection of neural activity, which has found use in magnetoencephalography. So in NMR we use the same process. So vapor cell also promise complementary access of high energy physics by detecting anomalous dipole moment from coupling to exotic elementary particles and background field beyond the standard model. So you can see here, this is the representation of the essential element of the atom based sensor, which require a light source, vapor and detector. You can see left hand side a laser beam will fall upon it. In between that we are having a atomic vapor, and right hand side we are having a detector that is detected by the photodiode. So it is very easy just to see the atoms based. This is the vapor of the atoms which is inside a atomic element. So these are the representation of the essential elements of any atom based on the sensor which requiring a light source, vapor and detector. Now the image illustrates the fundamental setup of an atom based quantum sensor, and this atom based quantum sensor utilizes the interaction between the laser light and the atomic vapor to perform the highly precise measurement. Means we are using the laser light that will fall upon the atom and that will measure the various parameters. So a laser beam is tuned to a specific atomic resonance frequency to interact with the atoms in the vapor cell. So we require the atomic resonance frequency just to match with the laser beam. So the interaction can be measured by change in the light absorption or the reflective index or detected by the photodiode. Means various parameters we can find out when there is an interaction between the laser and the atomic vapors. So this setup can be used for sensing various physical quantities like electric field, magnetic field or the time period or the frequency. So such sensors are noted for their high sensitivity, stability and reproducibility, like because all the atoms of the same species are identical quantum system. Vapor phase atoms manipulated and probed by the light, and either we are using the electromagnetic field, so constitute a versatile and powerful quantum platform for the sensing. So vapor phase atom manipulated and probed by the light and other electromagnetic field, so that constitute a powerful quantum platform for sensing. So the energy level of most atomic states are known to 8 or more significant digits of absolute accuracy. So their dependence on the external field can also be predicted with the high precision. Extremely desirable properties of the sensing. So a very sensitive or a very low magnetic field can be measured by using the vapor phase atoms. Now you can see here, these are the you all know that in the laser system we are having the two levels that is defined as atomic transitions between the lower level to the upper level. So delta E is equal to HF, change in the frequency. So depiction of the rubidium atom showing outer shell 5s1 by 2, which is in the red color, and the inner shell that is represented in the blue. Left hand side diagram you can see, and of the electron. Similarly, the line is also here defined. Inner shell is defined by the blue line and the outer shell defined by the red line. So there is a transition which is representing the photon interaction on a simplified two state atom. So there is a atomic transition between the two level, outer and inner shell. So both conceptually and quantitatively, consider each atomic state of the energy En to be represented by the de Broglie clock ticking at the frequency En, which is equal to En by h, where h is the Planck's constant, and measure the outcomes depends only on the energy difference. And we know that the rare exceptions where the atomic sensor measure the Bohr frequency, that is F and M. That is the difference between the two frequencies of the different levels, like Fn minus Fm, via the interaction with the light or the field of frequency. That's why frequency, which is equal to the difference between the two two levels, that is a F and M, that is a Fn minus Fm. So for atoms in the vapor phase, these stable and predictable energy difference result in the high inherent precision and absolute accuracy for either stable reference standards clocks or the well defined shift from the environmental perturbations, which is the electromagnetic and the inertial sensors. So the most attractive feature of the atom based sensor is that they offer the opportunity to produce measurement with excellent sensitivity or the long term stability. So the opportunity, we can say that opportunity means we are emphasizing, because the performance of a sensor depends heavily on how it is implemented. Means atoms not only have the fixed predictable properties, but also many atomic states have narrow line width and enabling features for high sensitivity measurement. So narrow line width and atomic states, narrow line width in the atomic states are also the one of the requirement just to measure the high sensitivity, just to measure the low magnetic field or LO parameter with the high sensitivity. So transitions tied directly to fundamental atomic structure enable atom-based sensor to serve as a standards that do not rely on external calibration for the stability and the accuracy. So atoms make excellent quantum sensors because why we are using the atom and we are making the quantum sensor, and we are saying that these are the excellent sensors. Why we are calling? Because they are having the four fundamental features. Number one, identical. Number two, isolatable. Number three is interfaceable, and the fourth is intangible. So these parameters or these features are required, which makes the atoms excellent quantum sensors. What are these identical? Atoms of the same isotope are identical. So well defined atom sensors can therefore be insensitive to manufacturing variations of the primary sensing element. So leading to the reproducibility, that the principle is directly traceable to the fundamental immutable properties of the atom. So identical atoms of the same isotope. Second is the isolatable, that in order to realize the stability and accuracy of the sensor, atom must be well isolated from the sources of systematic errors. it must be isolated, and if it is isolatable, so it can be it can get the more accurate result with the great stability, because it is free from the systematic errors usually arising from their interaction with the outside world. So, in order to realize the stability and accuracy of the sensor, we use isolatable. So, next is the if we talk about the wall interactions, represent one such connection where the laser cooling and trapping can completely isolate the atom from the walls. It should not be interact with the walls. So, laser cooling and the tapping is a perfect example for that. So, remarkably, even a warm vapor confined in a glass cell remains sustainably insensitive to energy shift from the wall collision. So in cooling and in the trapping we use. Another is the stereoelectromagnetic fields can be shielded to some extent, but their well understood interactions often allow atomic sensor to reliably manage their systematic effects, so that it can be isolated and it cannot be interact with the walls. So, example is the atomic clock. When we just discuss the atomic clock, then we will find out that the energy difference between the two clock energy levels is independent of the magnetic field. So, uniquely atomic vapor allow direct quantum measurement of inertial quantities through the manipulation of the momentum states. So, these are the two features. Now, the next feature we will discuss in the next lecture. Thank you very much.